In this next reaction, we are going to look at a new style of reaction where we have a molecule called NBS, which stands for N-bromosuccinimide. Now there is a bromine, that's a key reagent. This is indeed a replacement molecule for a reaction where we were able to do bromine in water. So this we'll look at what is the advantage of NBS H2O reagent versus Br2H2O. Okay, so if you remember bromination or Bromohydrin formation reaction, where in the medium of water or aqueous medium we have done this reaction, and we found out that the bromine does add here, creating a carbocation, but bromide ion that was kicked out, which is aquated or solvated, is no more interested in doing the nucleophilic attack. Instead, we were able to create an alternate or a competing nucleophile, which for obvious reason, because of bromine electron sphere, it essentially came from this side, right? And this was a stereo restrictive process. So OH2 or H2O, the nucleophile, did not come in, and it after a couple of steps, of course, let me finish the steps if you have forgotten. So we will have a OH plus, and this signifies, having this wedge and this dash signifies that we have come from the opposite side, and a second molecule of water is going to function as a base to escort that proton. So eventually we get a molecule called bromohydrin. Now bromohydrins have a very unique use in synthetic organic chemistry. So there is a problem if we use this method. What is the problem? The problem is we are assured that we are going to get majority of the product like this. However, that bromide can still function as a nucleophile under rare occasion, and it can produce a minor product of dibromo. So this is a possible minor product. This is major, of course it's major, but there is a minor contaminant that we might get. To avoid this, we want to maximize this bromohydrin. Maximize bromohydrin production. So what we are going to do is we have an alternate reagent called N-bromosuccinimide. N-bromosuccinimide is this. It is. The structure may not be important, but can be important, especially when you are parsed during the exam. If there is a test coming up, and if somebody writes NBS and you know it's just a N and bromo, this is a N-bromosuccinimide. Okay, this is NBS. The nitrogen bromine bond is polarized this way, delta minus, delta plus. It's polarized that way, right? So that means if there is an alkene, right, this alkene is not interested in nitrogen, it is interested in bromide. So that is one advantage of NBS. Otherwise we relied on a polarizability factor there. So this is a natural polarity. So the process is pretty much the same. We are going to get the same intermediate as in the previous case. So we are going to get same intermediate. Remember, I have already done the regio selection by saying that I'm going to get a positive charge on that carbon, not on that carbon. We already did the selection. So that part we have already taken care of. Now, of course, what is left behind is this contraption. This contraption is so big and it's not interested in reacting with this carbon. There is a negative charge. That negative charge is not going to be interested in that positive charge. That means whatever minor product we got because of that contaminant bromide, now this piece is not interested. So we are going to get 100%. 100% of our reaction is focused on that attack, right? Of course, the stereo selection crosses that. Ultimately, by the same mechanism, I'm going to skip 2 steps, and ultimate product is definitely that. So this is 100%. Okay, 100%. So while this could be 98.2 or 99.1 or 95.5, depending on the temperature, depending on the conditions, depending on the amount of HBr or some amount of bromide you used or vicinity. So the advantage of using NBSH2O in bromohydronation, this is a halohydrin, bromohydrin. Okay, there is a counterpart NCS, and you know what C stands for. It's a N-chlorosuccinimide, so which can also be used for chlorohydrination. I don't have to redo this. In NCS instead of NBS, NCS is going to be chlorine here, and the game is still going to be the same. Okay, so this is a variation of bromohydrination. Here we are maximizing one of the products. That there is a interesting side effect or side use of NBS. So whenever we take a alkene, whenever there is an alkene, we know that there is this carbon, this location is called allylic, while these carbons are labeled what? Vinylic. The carbons involved in a pi bond are called vinylic carbons. Carbon one place away from pi bond is called allylic carbon. Now allylic is a conjugation system. Remember, allylic means to have a conjugation, you have to have a pi location or pi availability in allylic location. So that is a potential conjugated location. So essentially what happens is, when you take NBS and sometimes even bromine, we can even use bromine, NBS in presence of H-nu. And what H-nu stands for in organic chemistry is, it's a Planck relationship. This simply represents photochemistry. What does photochemistry mean to you? Photochemistry means UV light. UV light is used to cleave nitrogen-bromine bond. So here we have a radical reaction. So the process is going to be a little bit crossed now. This is not going to be polar reaction anymore. This is not going to be our natural process, our non-usual reaction. Actually, this reaction gives you it leaves this one intact, pi bond intact, and gives bromine substituted in this location. So this is called allylic bromination. It's called allylic bromination. When we have a super allylic, when I use the word super, I'm talking about benzylic location. There are 2 hydrogens here. These are called benzylic carbons, right? It's very similar to allylic. Same thing is true if we use NBS, H nu. We are going to get one single substitution in benzylic location. Okay, so this is called benzylic bromination. Benzylic is also allylic, except that there is a benzene ring which is giving that allylic. This is called benzylic bromination. Okay, so what would be the mechanism for that process? Okay, so let's look at radical mechanism. Radical mechanisms go through three different stages. One is initiation. Second is a set of propagations, at least two of them. Propagation 1 and propagation 2. And then finally termination. So when we are doing radical reactions, we should not get, there is no cations or anions. Okay, there are no cations and anions. Typically solvent use this non-water, so it's a non-aqueous solvent. Okay, right? Radical reactions will not have cations or anions, they only have radicals, and radicals are units that are not charged. They are not charged units. They are not charged. Not charged. But they are electron deficient. They are electron deficient because radicals are one electron away from typically the octet business. Alright, let's look at what is the initiation in this case. So let me rewrite the reaction. When we take, let me give you a spiel on the complication in this reaction. So if I have that, how many allylic locations do I have? I have that one to be allylic, that one is allylic, and that one is allylic. Those are three allylic locations. So if I did react with bromine or NBS, sorry, we could use bromine here as well, H nu. So first get-go, we should be getting three products. We can have bromine here, we can have bromine there, and we can have bromine there. That is a preliminary level. Once you look at resonances that radicals produce, this can also give you another, a pair. This will give you not this molecule. When a radical is created that leads this one, along with this product, there is another product created. And we will learn to justify this. The same intermediate that gave you this also can give you this. And you already see there is a mess coming up. And same intermediate that gave you this will also produce this. I shouldn't be saying equal because this is not going to give you this. I should not use that equal. So these two pairs, each of these pairs are created from same intermediates. That's the right way of approach. So this is going to give you that. How are you going to justify this? How are we going to justify formation of the 6 molecules, out of which of course this one and this one happen to be identical? And you can see these two are identical in structure. Okay, but that's besides the point. There is a 6 possibilities, right? And this is a complication that we need to worry about. Now, before I get to study about this complication, let's look at the mechanism first. Once we look at the mechanism, then we start analyzing the stability of carbocations, or sorry, radicals, no cations here. All right, initiation. Sometimes we use something called radical initiators. Radical initiators are like hydrogen peroxide or peroxides. They can initiate a radical. It's like striking a match. When you strike a match, that can propagate the fire. Okay, so we have an NBr bond. That is the one that we are focusing on, and rest of the contraption are just for the sake of. Okay, so whenever there is a UV light, there is a homolytic cleavage of this bond, and you see we are showing with a single hook that shows one electron moving this way, one electron going there. Okay, the bond NBr is homolytically cleaved, giving you a nitrogen radical with connected to this gigantic piece, which is not interested. It is stabilized because that radical can resonate here. That is occupied in the business because it can resonate. Radical goes there, it keeps hopping. This radical is not reactive, but this radical is one that spreads. Okay, this is the one that spreads the fire. So this is the initiation. Propagation would be propagation number 1. Now what this bromine radical has to do is find the weakest link. So let me take this molecule, which will make our life easier. So there are 3 hydrogens here. There are 2 hydrogens here. There are 3 hydrogens here. And by nature, these 6 hydrogens are equivalent. These 2 hydrogens are benzylic hydrogens. These are, once you create a radical here, if this bromine radical comes and grabs this hydrogen, puts the electron there, that's a miserable radical. Instead, that bromine comes and threatens this hydrogen to come with it. So by one of these, it doesn't matter which one of these 6. Okay, so I'm going to isolate one of these hydrogens for my game, right? So propagation 1 would be bromine radical coming along, demanding that this hydrogen bring 1 electron with it, leaving behind 1 electron here. Because each bond has 2 electrons, 1 electron will stay on this carbon. And typically hydrogen doesn't want to go away with carbon, with the electron. This carbon wouldn't allow it to go away, but bromine has demanded it. So what we have now is HBr is produced, because Br and H marry together, make HBr. And remember, this is a non-aqueous solvent, so they are happy to live together. But it created a new problem. Now this carbon is radicalized. This carbon is radical. The fact that it is an allylic radical, it can resonate. How does it resonate? This electron comes here, 1 electron from here goes there to make a pi bond, other electron comes and sits there. This is how we delocalize the pain. This is how we delocalize the pain. That's a what? That's a resonance. That arrow shows resonance. What do we get at this stage? You will have a double bond there and radical is here. Now interestingly, they may look alike, but these are 2 unique radicals. In this particular example they are not, but in this case you are going to see that they are going to be different. Now this radical, this system is going to keep on hopping back and forth, since this is a delocalized. Okay, now this delocalized radical, this is propagation step number 1, goes through propagation step 2. Propagation 2 what does this do is, let me take the first radical itself. What this does is it demands that bromide, these are all statistical chances, and again, if you are asking me why did that happen, I will simply say because I saw this as part of somebody else's explanation, because I personally did not see that happen, but it has been well established that this is what is happening. Scientists have figured it out. So bromine is going to then react here. Right? Now, had it been this radical, you would have had that. Right? If this was the radical, you got that. If this is the radical, you got that. So those are the two possible products, propagation. Termination is something that we should not have to focus on this particular example. Termination is, what do we do in the end? When we created radicals in this particular system, who are all the radicals that we have come across? We have come across that radical. We have a nitrogen, and I'm going to write like this, radical, and we have a bromine radical, and we also have, which other radical? We also have that radical. Those three are the players in this game. So termination must be involving one of those three or more than one of those three. That means depending on who is in excess, it depends in the end, whoever is in excess. When all the molecules that we started with, starting molecules were what? Starting molecules were these. If you remember, starting molecule was this plus this. Those were the two things that we placed in the pot. Right? This one and this one are added to the pot, and sunlight or UV light was flashed on it. And one time. It doesn't have to be, continuous process. Once we finish that, all those starting molecules have reacted. In the end, you will have these three possible radicals are remaining. Either this is going to be in excess, or this is going to be in excess, or this is going to be in excess. Depending on who is in excess. If these two are in equal quantity, this one will kill this one and make a bond. If these two are in excess, this one and this one are reacting and they terminate each other. If this is the only thing this is in excess, it's going to react with other molecule of the same thing and terminate. Bromine and bromine can terminate themselves. N and N can terminate themselves. So there are 6 possible products, right? This one to this one, this one to this one, this one to this one, and then this one with this one, this one with this one, and this one with itself. So there are 6 possible terminations, and we don't really worry too much about which one is predominant. Ultimately, we are focusing on what did we get, because we are looking at what happened to carbon molecules. Now let's go back and look at what happened here and what is the thermodynamic significance of that. Okay. Before I get to that particular example, let's look at which of these. If I start radical formation, this, suppose it goes through radical formation, right? And they are both going to be allylic locations. Is that correct? These are allylic locations, right? So if I remove the hydrogen from here as opposed to here, okay? So the 2 possible radicals we are going to make are that one or that one. Okay. Now comes the issue. Which one is predominant? Which one is going to be more prevalent? And we have, at some point we have learned that CH3 radical, primary radical, CH3 radical is less stable than primary radical, which is less stable than secondary radical, which is less stable than tertiary radical. Put numbers I usually like to say primary to tertiary is like a 10 to the 6 times advantage. Primary to secondary is, we remember the reactivity factor and selectivity factor, 10 to the 3 advantage. And methyl to primary is about 100, 10 to the 2 advantage. So what does that mean? What does that mean? That means compared to methyl, primary is 100 times more stable. Compared to primary, secondary is 1000 times more stable, right? 1000 times more stable. And compared to secondary, tertiary is 1000 times more stable. In terms of energy diagram, right? If methyl radical is here, primary radical is more stable, secondary radical is further more stable, and tertiary radical is most stable of the 3 radicals, right? Now, if that is the case, let's imagine transition states that lead to that radical versus that radical versus that radical versus that radical. Right now we have a primary radical and a secondary radical are posed in front of us, right? This radical is secondary, this is a primary radical. So to get to primary radical, my transition state has to be at least that high or slightly higher, right? To make a secondary radical, do I have to go that high? No, I can squeeze right there. I don't have to, my transition state doesn't have to be as high as this one. And similarly, to go to tertiary radical, I don't have to climb that high, I can just go like this, right? So the transition states are going to be decided by the intermediate stability. So if the reaction goes via a primary radical versus secondary radical, you can see secondary is going to be 1000 times more favored over primary because I gave you those numbers. If there is a road that can take you this road, why would it go through this road, right? It's like if you are reaching home in 5 minutes, there is a road that take you to your home or a destination in 5 minutes. Why would you spend 2 hours for doing that? Unless you like to drive, unless you don't want to go home. Normally, we would like to reach the destination or our product reaction has to be finished quicker. If you are doing an experiment in the laboratory, nobody says that, oh, I worked for 3 hours to get this, and somebody says, I did it in 5 minutes. Well, that person will be hired and you won't. So essentially, when you have a road that is available to go to secondary route, why do you choose primary? So molecules are not allowed to go through that route. So this is again regio selection. If there is a radical available, if this possible versus this one, this is going to be a minor process. This is not going to be a major process, it's going to be a minor process. Better yet, think about it this way. Think about it this way now. I'll give you another example. And you see it is a buffet. It's a buffet of radical choices. There are 3 choices here, right? There are 3 choices here. When hydrogen can be removed from here, if it is removed from here, that will be primary radical. So 3 possible radicals that can be created in this case are, see, this type of analysis is essential to be able to look at what is the predominant product. That is one of the radicals. If I remove that one, that would be one of them. What would happen if I remove that hydrogen? It will give you that radical. If I remove this hydrogen, what do I get? I'll get this radical. Now, after looking at this, you are going to say, this is the last thing we are going to do. And this is also not a favorable one. Between these two, this was this was highly favored. But when this option is available, these two are not going to be chances. These chances are not taken. So whenever there is a tertiary location available to remove hydrogen, the molecule will grab that option. Because again, profitability in the reaction. Thermodynamics means how little energy are you going to spend to get on the other side of the reaction. That is the thermodynamic aspect of a reaction. So if I take this molecule and treat it with NBS H nu, first of all, not that they are not going to happen, not that they're going to happen, they are going to be tiny minor, right? This is the major. Major means I would go 98%. I would go 98%. And these two together are going to be 2%. So is it worth worrying about them? No, not necessary. Okay? And that's what's the beauty of it. Even though there is so many things that can be happening, nature picks what is the easiest way. So while it can go through this road, why would it allow molecules to go this road? This is a wasteful energy, wasted energy. So the product we are going to get, or we are poised to get, now we know that this is not going to be the final product. You will see that this is not the final product. Okay? The product we are poised to get is this one. Okay? We are poised to get this product. However, there is another product based on stability of the molecule, stability of the final molecule, we get this product. And I believe you have learned this concept before. How did we manage to get this product? Now, it is possible to say H has gone from there. So let's look at how did we get this one. I'm not going to worry about all other options. Okay? How did we get this one? And why is it more stable product than this one? Anybody wants to tell me why this is more stable? This is less stable. But this is more stable intermediate. So let's see what is the radical that led to this. This was the radical that was formed, which resonated to give you that radical. Now we know this is a tertiary radical, this is a secondary radical, right? That means if I show a mini energy diagram, right, starting from this molecule, so let's say I am here, I went to a secondary radical, tertiary radical. Let's say this is my A and this is my B. B can resonate to become C. And what do you say about C? C is higher in energy. Why is it higher in energy? It's a secondary allylic radical. But there is an interesting reason why, even though it is less stable, it produces more stable product compared to what this is going to give you. How do you know that what you get from here that's a D, and from here you are going to get, let's say, E. So that's a E and that's a D. This is A. Okay? So this is A as a starting molecule, forms a radical, tertiary radical B, which resonates to give you secondary radical, which is less stable, which is C. Now B can give you final product D, which is this one, but E is produced by reacting C with the bromine radical. So what is making, this is the thermodynamic stability, while the intermediate is less stable, the product, this is more beautiful place compared to this one. So a little bit of expenditure here is not a big deal considering what gain you are going to have. This is the ultimate profit. Okay, so reactions sometimes go through this type of profit making business, and this takes a little bit extra time. This is a fast product, this is a slow but more stable product. That's called thermodynamic and kinetic control. So if you raise the temperature a little bit, you get 99.9 or 100% of this. If you do it at a lower temperature, you might get this as a product. Okay, and that's something that we will discuss in a different lesson. So what makes this more stable? Did you get it? Well, this is a tetra-substituted alkene, while this is a tri-substituted alkene because there is a hydrogen here, right? And you know, tetra-substituted alkene is more stable than tri-substituted alkene. That we have discussed in a previous discussion. So stability of alkenes, and if you really want me to restate that order, stability of alkene is, this is the order of stability of alkene. Unsubstituted is less stable, monosubstituted is more stable than this one, which is less stable than disubstituted alkene. Among disubstituted, this is less stable than this one. A cis disubstituted is less stable than a trans disubstituted. We have done this before. And which is less stable than tri-substituted alkene, and which is definitely more stable, less stable than a tetra-substituted alkene. So this relationship, this stability order, this is the most stable alkene, and we have discussed this in light of hyperconjugation. I think we talked about hyperconjugation as a logic behind explaining this, and later this comes as a aid for, we use this concept for something called Zaitsev Rule. Zaitsev Rule depends on, and we are going to come across that, so I just wanted to keep that in mind. We are going to use this concept for something called Zaitsev Rule, where more stable alkene is most substituted alkene. And how do we know this? We just know this. How do we know this? We just know this. Okay? And people have figured out by variety of reactions that a molecule, a process that leads to this product is going to be more favored than this product or this type of product. Okay. So when there is a radical process, there are multiple possibilities. Now, if I look back in this example that I concocted, right? We have overlooked lots and lots of different facts, right? So we will take some other time to analyze this one. But keep in mind, in radical reactions, there are no charged bodies. There is no cation, there is no anion, there is no carbocation, there is no electrophile, there is no nucleophile, nothing. These are radical substitution reactions. This is not addition reaction. Why couldn't this be called an addition reaction? Why could not this be called an addition reaction? Because addition reaction should result in a pi bond being destroyed and 2 sigma bonds being created. In this case, pi bond still stays as is. Pi bond did not go away. In the product, there is still a pi bond. That means this is not an addition reaction. So let me go back and restate this. If you take this, react with NCSH nu, the product that is a radical substitution reaction. What is substituted? There used to be a hydrogen here. That hydrogen is removed and chlorine is substituted in its place. Okay, it's a substitution reaction, not an addition reaction. For that reason, this reaction doesn't fit our previous conversation, because all our alkene addition reactions, we thought they were electrophilic addition reactions. In this case, we retain the pi bond. Okay. Now, keep in mind, we could do the same thing if you use Br2 H nu, we will also get this. Okay. In this case, I did not show you the choices because both of them are going to be primary, so we didn't have to fuss over it. Okay. Now, keep one thing in mind: when there are multiple locations of pi bonds, now then you have to be mindful about which intermediate is more stable. So, a question on a test, if this is offered to you as a question on a test, you should feel good. This question is an easy question to answer. See, I'm showing the variety. We can use NBS, NCS, I2, same thing, because iodine radical can be created in presence of sunlight, right? Once that radical is created, it has a choice of taking hydrogen from here, hydrogen from here, hydrogen from here. Now keep in mind, are there hydrogens here? Yeah. Are there hydrogens here? Yeah. Are there hydrogens here? Yes. But then why didn't we touch those? Because hydrogen here is not allylic. Allylic ones can be resonating. Anytime there is a resonance, the radicals can stabilize. So it is critical for us to note that this reaction can only happen on this location, or this location, or this location. Okay? Don't be tempted to do a reaction here. Do not get tempted to do the reaction here. Don't be tempted to replace a hydrogen here. Don't do reaction here. Don't do reaction here. Because there is a lot of choices available for you to replace. Even then, even when these three are available, which one are you going to pick for the highest? You are going to pick this one to be the predominant. This is going to give you tertiary radical. This is going to give you primary radical. This is going to give you secondary radical. So essentially, if I have to pick one product, it will be this one. It would be iodine on this carbon. Okay? And the other product you might have to pick in the choice, suppose there is a multiple choice offered, the other product is when you do the resonance, you get a radical here, which gives you, for an obvious reason, you are going to get a more stable product. So this is more stable product, iodine here. Okay? Iodine here. Remember, this is CH3, this is CH3. You don't have to write anything there, it's understood. But iodine here, these two are acceptable products in this reaction. Okay? And if I wrote NBS, it will be bromine here and bromine there. So either one of these are the products. Now, if the test maker, I'm not always the test maker. The test maker writes cold here, cold condition. In that case, this will be predominant. If somebody writes hot, then this is the predominant one. And that aspect we will learn some other time. Okay? So this concept is finished in this story. Now, before we leave, also be aware that when you have something like this, again, there are a bunch of hydrogens on benzene ring. There are a bunch of hydrogens on benzene ring. These hydrogens are off limit. Don't touch any of them. There are these hydrogens here. They are off limit because their pK is very high. There are D hydrogens. These are off limit to be substituted. The only ones that you can substitute are these hydrogens. Okay? Because these are the ones who can resonate because they are allylic or benzylic location. So if you take this molecule and it may sound today, it may make sense, but when you are posed with a question like this, and you have to pick one answer, and the answer is obvious at this point if you are prepared. If you are not prepared, answer is not obvious. Then you have to hunt and pick what works at that moment. The answer is that one. This is the only answer you should be able to pick. This is the only answer you should be picking. What are the other answers that you should not pick? Other answers that would be written should not be picked are that, or that, or that, and I can go everywhere here. So these answers are wrong answers. Keep that in mind. Allylic bromination. This is the allylic bromination or benzylic bromination. That means this is the location that we should be looking at. Right? And the last glitch or last what do you call twist to this story is, what if I have something like this and NBSH nu. Now we are going to say this is benzylic, this is benzylic, this is benzylic, and we don't have a reason to discard any one of them. They are all equivalent. So when we use NBS, we are not going to pick and choose. We are going to say the final answer is going to have, unless I limit you to monobromination, there is no reason why there is only one bromine add. So all three locations can have bromine added. Okay? The correct answer for this question, this plus this gives you what? This is the answer. Don't try to do it here, don't try to do it here, don't try to do here or here or here. And only allylic or benzylic location. Benzylic means one place away from benzene ring, which is simply one place away from pi bond. So this is the answer. Okay? So you don't have to limit to only one of them in this case. This is secondary, this is secondary, this is primary, I'm going to pick this one. Not necessary in this case. You are going to say that is, since I did not say how many NBS are added, if I limit, give the, if I told you, if I specified, say that give monobromination, then you can pick, you can avoid adding bromine here, you can add here or here, because both of them are secondary. Okay? Otherwise, it is a buffet. You can use any one of them. Alright? So this conversation is finished.